There is a mystery at the heart of our universe. A puzzle that so far no one has been able to solve.
This is too weird.
Welcome to my world.
If we can solve this mystery, it will have profound consequences for all of us.
That mystery is why mathematical rules and patterns seem to infiltrate pretty much everything in the world around us. Many people have, in fact, described maths as the underlying language of the universe.
But how did it get there?
Even after thousands of years, this question causes controversy.
We still can't agree on what maths actually is or where it comes from. Is it something that's invented, like a language, or is it something that we have merely discovered?
I think discovered.
Invented.
It's both.
I have no idea.
Oh my God!
Why does any of this matter? Well, maths underpins just about everything in our modern world. From computers and mobile phones to our understanding of human biology and our place in the universe. My name is Hannah Fry and I'm a mathematician. In this series, I will explore how the greatest thinkers in history have tried to explain the origins of maths' extraordinary power.
You ruined his equation.
I'm going to look at how, in ancient times, our ancestors thought maths was a gift from the gods. How in the 17th and 18th centuries, we invented new mathematical systems and used them to create the scientific and industrial revolutions. And I'll reveal how, in the 20th and 21st centuries, radical new theories are forcing us to question once again everything we thought we knew about maths and the universe.
The unexpected should be expected, because why would reality down there bear any resemblance to reality up here?
In this episode, I explore paradoxes within modern mathematics.
Who shaves the barber?
And I discover the very weird worlds that maths seems to be leading us into. Maths is very much part of our modern world. Even the images you're watching now are essentially numbers processed by computers.
Sorry, guys. Would you mind taking a photo of me?
Oh, sure.
Give me 1 second.
Today, maths is at the heart of big business in the development of new software, such as facial recognition technology, all of which, fundamentally, is based on mathematical algorithms. And it matters because copyright issues and legal ownership can depend on where that maths comes from.
You can phrase the question like this. Is maths a genuine, fundamental part of our universe, something that we have discovered? Or is it merely invented, a language that we've created just to describe the world around us?
Mathematicians have argued over this idea for centuries, and even today, this question is a thought-provoking and challenging dilemma. So far, I've explored how, in ancient times, maths was revered as a gift from the gods, perfect, complete, and gratefully discovered by humans. But through the ages, new areas of mathematics, like algebra and the concept of zero, have quite simply been invented. But for most of us, we normally think of maths as just a series of objective facts based in logic that someone somewhere has discovered. Facts that we all start to learn at school.
If you're anything like me, you'll remember maths at school being taught has a series of rules that's very logical, it's very ordered, very complete, very black and white. There were right and wrong answers, which you didn't necessarily get in other subjects like art or like music, which were much more about preferences, about opinions, and about cultural differences.
It felt like the mathematical rules were intrinsically true. But why? What are the fundamental mathematical laws? To answer that question, you have to categorize everything. You have to boil maths down into distinct groups of objects in something called set theory.
Set theory is a language that talks about groups or sets of items. So, for example, the set of odd numbers are all the whole numbers that cannot be neatly divided by 2. And the set of even numbers are those that can.
This reveals a basic rule. Adding an odd number to an even one produces an odd number. From simple rules like these, you can build up more and more complex rules and relations of maths. But there's a problem with set theory, a paradox at the heart of mathematical rules which caused a bit of a crisis at the start of the 20th century. You can discover this paradox yourself by going to your local hairdresser or gentleman's barber and trying to define what you find in a concise and complete way.
Hello.
Hello.
I was wondering if you could help me. I am looking for the very definition of a barber.
I think I can help with that.
Mathematicians took the same approach to precisely define the laws of maths.
So if you were looking it up in a dictionary, like one sentence that defined what a barber was, what would you say it was?
Cut men's hair.
Cut men's hair. But that could be a hairdresser though, right? Hairdresser. It needs to be a unique definition for barbers. Barbers and only barbers.
There's shaving element as well, isn't there?
Yeah, that's true.
I've never had a shave in a hairdresser's.
No, that's true.
Chat.
The chat. Yeah, it's a very important part of it.
You do hear some stories being a barber.
So actually, I suppose the shave thing is something that only barbers do. So someone who shaves men.
But a barber doesn't shave all men, and I need a phrase that uniquely and completely identifies a barber and no one else.
Okay, let's see where we are then. So we've got a barber shaves all men, but only the men who shave but don't shave themselves.
Yes.
All right, I think we've settled on something now.
We've agreed on a barber shaves all men and only those men who shave but do not shave themselves.
Sound about right? I mean, it doesn't exactly roll off the tongue, but I think it's fairly accurate. But hang on a second. There's a bit of a paradox here. Who shaves the barber?
Well, can a barber not shave himself?
But if he does shave himself, then our definition here says that he doesn't shave himself.
Let me clarify that. If he doesn't shave himself, then according to the definition, he's one of the men shaved by the barber. So he does shave himself. Attempting to create a mathematically precise definition creates a contradiction where the barber both shaves himself and doesn't shave himself.
Push the bristles into the face.
This is known as the barber's paradox.
You got it.
I did it perfectly.
Perfect, okay.
It is an illustration of the paradox at the heart of mathematics, which was discovered in 1901 by one of my favourite troublemakers, Bertrand Russell. The problem for maths was that Russell's paradox undermines the logic of defining things, like odd or even numbers, by putting them into categories or sets.
Over here, I have got a set of clipper attachments. And in there, I have got a set of things that aren't clipper attachments. Clipper attachment goes in there. Not a clipper attachment goes in there. Clipper. Not a clipper. Now the question is, where does this bag belong. It's clearly not a clipper attachment. Is it going to attach to a clipper? No, it's not, which means it needs to go in there. But we've got a problem, because this sink is supposed to only contain things that are not clipper attachments, which means that the contents of the bag can't go in the sink.
Since the bag, or set, is not in itself a clipper attachment, but by its definition contains clipper attachments, we can't easily categorise where the set belongs. Similarly, the barber can't, in a logically consistent way, be contained in the set of people that do shave themselves, or the set of people who don't. Russell's paradox shows that there is a logical problem with trying to categorise anything into coherent sets, whether it's barbers, clipper attachments, or even numbers. And this logical puzzle exposed a fault in the bedrock on which all the rest of maths is built.
If the foundations are shaky, how can we trust everything else?
Bertrand Russell realized that mathematics was on much shakier ground than people had originally thought. It turned out to be much, much harder to really lay a solid foundation for math that everybody agreed on. And this is still wonderfully controversial to this day.
That's what you do in science and mathematics. You take a sledgehammer, you smash at whatever structure, whatever edifice you've built, you try to find the weaknesses, and that allows you to figure out what needs to be shored up. And that's really, I think, the legacy that Russell left us.
I think of it as, in some ways, the death knell, or at least a major challenge, the attempt to ground mathematics in logic. And that's the thing that becomes really hard in light of Russell's paradox.
Russell's paradox caused a real crisis amongst mathematicians. Suddenly, maths was uncertain, was fallible. And if it has these fundamental problems, how can it possibly be discovered? So does that mean that maths has to be invented? Just a human language and all of the flaws that come with it?
If maths is merely an invention of the human mind, it's perhaps not that surprising that it's not perfect. But I don't think I'm ready to accept the invention argument quite yet. Maths just seems to be too good at predicting the behaviour of the world in ways we never could have imagined. Because just as Bertrand Russell was exposing the limitations of maths in one way, another titan of the 20th century, Albert Einstein, was pulling it back in a completely different direction. Take what is probably the most famous equation in the world. With just 5 symbols, it looks so simple, it's almost childish. Yet it contains some incredibly powerful mathematical and philosophical concepts. I'm talking, of course, about E equals mc squared.
What's it?
So E, that's energy, that is equal to m, that's mass, times by a constant c, that's the speed of light, squared.
There is so much more to this equation than meets the eye. It is Einstein's discovery that matter and energy are equivalent, and that has profound consequences.
This equation gives us one of the immutable laws in the universe, that nothing can travel faster than the speed of light. Which on this one.
The reasoning is this.
Making something move requires more energy than keeping it at rest. And because this C here is a constant, if the energy goes up by accelerating something, the mass also has to increase. So that means that you or I actually weigh a tiny bit more when we're moving in a car or a plane.
The increase in mass only becomes significant when objects are moving at speeds close to the speed of light.
as an object approaches the speed of light, its mass rises faster and faster, which means it takes more energy to accelerate it further. It can't therefore reach the speed of light because the mass becomes infinite and it would require an infinite amount of energy to get there.
You've ruined this equation. As well as proving there's a cosmological speed limit, this single equation also explains how all the stars in the universe convert mass into energy as they burn brightly in the night sky. Einstein's famous equation has proved itself to be a remarkable match for reality every time it's been put to the test. Einstein had uncovered one of the essential mathematical rules underlying the cosmos. It seems like clear evidence that maths, at least, is discovered. But Einstein didn't stop there. Using the power of mathematics, he brought about a fundamental shift in our understanding of space and of time and of how light travels through space. To see that evidence for myself, I've come to an observatory to do some serious thinking about what we actually see when we look at stars in the sky, such as our sun.
If things were happening right now, we wouldn't be able to see it until 8.5 minutes later, because that's how long it takes the light to travel to the Earth.
So when you're looking at the sun, you're seeing how it was 8.5 minutes ago?
Exactly. And objects that are further away, we see them as they were further back in time. So, for instance, there are other stars in our galaxy that are thousands of light years away, so we see them as they were thousands of years ago.
So when you look in a telescope and you're seeing them how they were when people were building pyramids and Pythagoras was discovering his rules on Earth.
Exactly, and we can see things that are even further away than that. So galaxies outside our own galaxy, we see many of them that as they were 1 billion years ago or more.
Gosh, goodness. Does this work at smaller scales then? Is there like a limit to how big something has to be before this works? If you, I mean, I'm looking at you now, right? Light presumably is taking time to bounce off you and for me to see you.
Yes, it is, but light travels at an incredibly fast speed, 300,000 kilometers per second, roughly. So the time it takes to travel from me to you is very, very tiny fraction of a second.
But in theory, I am seeing you in the past.
Yes, you're absolutely seeing me in the past.
All of this shows that we can never know what the universe is like at this very instant. The universe is, remarkably, not a thing that extends just in space, but in time as well. This is fundamental to Einstein's revolutionary insights about our universe. He realized that the very concept of time is relative. That is to say, it depends on the position and movement of the observer. He worked it out by thinking about events that appear to be simultaneous.
So let's imagine that you're in a hot air balloon floating above the observatory here, and you're high enough that you can see a flash of light in London, say, and another one in Portsmouth. And let's assume that these flashes of light go off such that you see both of them happening exactly simultaneously.
So from where I am, it looks like they're both flashing the lights at the same time.
At exactly the same time. But if I were in an aircraft that was flying very fast towards London, I would see the flash of light in London before the flash of light from Portsmouth.
Using the inescapable logic of mathematics, Einstein realized that if an observer is moving towards one of the flashes, they would see that flash before the other one caught up with them. So for them, the flashes are not simultaneous.
But but I mean, they did go off together. Who's right? Am I right in the hot air balloon?
In fact, there is no way of saying that you are right and I am wrong in how we observe these events.
This is called relativity.
So our whole concept of time, our whole concept of timings, what happens first, what happens second,
comes down to where we are and how we're moving.
Exactly. So the concept of time is now inextricably linked to the positions in space and your movement through space. So this is why we can't describe space and time separately, but we have to put them together in space-time.
You can't separate the two.
You can't separate the two.
And that all comes down to this idea that Einstein managed to prove via thought experiments.
Yeah, that's the amazing thing about it. Purely through thought experiments and
a good bit of maths.
And a good bit of maths.
Yeah.
A very good bit of maths, yes.
Einstein was using the mathematics to make sense of the universe and claiming that the universe was nothing like what anyone thought it was. His concept of relativity flew in the face of what people had believed about space and about time for centuries. Whether that was the Greeks thinking that the universe was eternal and unchanging, or Isaac Newton's more mobile and mechanistic descriptions. Einstein took his thoughts even further, attempting to wrestle gravity into a neat mathematical law. He believed it was all down to the strange behaviour of space-time. And if he was right, as he laid out in the theory of general relativity in 1916, then gravity will even affect light.
If you've got a star shining light from over here, then you, the observer, over there, will receive it in a straight line. But if there's a massive object in the way, you might think you won't be able to see the star.
However, Einstein predicted that the mass of an object will distort the space-time around it, and anything moving through that warped space-time will have to follow the curves. This warping of space-time, Einstein said, is what we usually describe as gravity. We think of gravity as keeping the planets in orbit around our sun. In fact, he said, it's the result of the distortion of space-time near massive objects. And Einstein calculated the precise effect it would have on light.
So, the starlight, while still technically travelling in a straight line, will follow the curves of space and appear around the object.
Einstein predicted that, in exactly this way, we should be able to observe light from distant stars getting bent, as the stars pass behind our sun. But a theory is just a theory, an invention of the mind. It only becomes a discovery when proven by practical measurement or experiment. In the decade after Einstein's prediction, solar eclipses around the globe gave scientists the chance to repeatedly test his theory. The darkness of the eclipse allowed them to actually see stars passing close to the sun.
When scientists took the measurements, they discovered that light from a distant star was bending around the sun in exactly the way that Einstein had predicted. The mathematics of general relativity was correct.
With general relativity, Einstein completely upended our understanding of space, time, matter, energy, and kind of what else is there to the nature of reality. All of a sudden, we learned that mass and energy can warp the fabric of space and time in this beautiful, interconnected dance where the motion of matter affects the warping of space and time, which affects the motion of other matter.
We used to think of space as this boring, static stage upon which events unfolded. Then Einstein told us that space is itself an active player in this game, like a stretchy rubber sheet, and yet a substance perfectly described by beautiful mathematical equations.
I mean, how did he think of that? How did he think of something like this?
Einstein's description of gravity, the warping of space-time, accurately explains why objects stay in orbit, whether they're satellites around the Earth or galaxies around black holes. His equations are being tested and reproven every day. And without Einstein's general theory of relativity, modern communication, GPS or satellite TV systems couldn't even function.
Although this theory came from his mind, from thinking about the problem rather than from real-world experiments, it's still so good at predicting, so perfectly capable of describing what happened in the universe, that it must be reflecting some underlying mathematical truth. And this lends quite a lot of weight to the argument that mathematics is discovered, which is something that matches up with my own experience. Because when you're toying around with mathematics, it really does feel as though you're exploring something that already exists.
But if we accept that maths does already exist and is an intrinsic part of nature, then surely all the rules are out there waiting to be discovered.
In some ways, mathematics is quite a lot like a game of chess. So you have these very strict rules that you're not allowed to break, but within those rules, there are all kinds of opportunities to play around and be creative. The only problem is that in maths, no one tells you what those rules are. We have to work them out for ourselves.
Most mathematicians like a challenge, but this idea got blown apart at a maths conference in 1930 in the Prussian city of Königsberg, when two great mathematicians and their conclusions collided.
On the one side, you have got David Hilbert, a mathematical king in every possible sense of the word. This is an enormously well-respected man who laid down the gauntlet, asking people to come up with a fundamental set of rules on which every mathematical proof could be based.
On the other side was a young academic called Kurt Gödel.
In contrast to Hilbert, who thought that mathematics should be built from the ground up by humans, Gödel thought that mathematics was discovered. He believed that mathematical truths exist outside of us and that we have very little say in what we can find. That summit in Königsberg can be seen as a clash between those who thought that mathematics is part of our fabric of reality to be discovered, and those who saw it as a language under our control.
Hilbert was confident that humanity would soon know all there is to know in maths. But Gödel, who had also been trying to find the rules of maths, had come to the opposite conclusion.
In a side room at the summit, Gödel quietly announces that, in fact, however hard you try, there are always going to be some things that are unknowable.
There are always going to be parts of the mathematical game that can't be fully explained. And if you can't know all the rules, how can you play the game?
According to Gödel, any rule-based math system is always going to have some things that are either unknowable or unprovable. And what's more, he could prove it. It's kind of ironic, if you think about it.
This was quickly accepted and became known as Gödel's incompleteness theorem. And it puts an interesting twist on our key question. It shows that even if mathematical rules truly are part of the universe and we're simply discovering them, we are nevertheless going to have to accept some of those rules without knowing how or why they are true.
Normally people think that there's some intrinsic difference between science and math on one hand and faith-based belief systems on the other. And yet what Gödel's theorem tells us is that's not true. That there are things in mathematics that you have to take on faith or you can't do the mathematics. To me, this was an astounding thing to realize.
We're going to have to accept that we can't give maths a foundation in formal rules or in logic in the way that we thought we could.
I think it's enormously exciting that math, in some sense, is open-ended. So in a sense, it puts an end to one way of thinking about mathematics, but I think it actually adds color and richness to the subject because it's just going to keep on going.
So what does Gödel's incompleteness theorem mean for our view of the universe and the parts that maths plays in it?
Well, it depends on what you're trying to use maths for. If your goal is to use it to describe what's around you, then it still offers a very detailed picture, enough to navigate your way through the universe and to explain its features. Sure, the map is not going to be the same as the terrain, but even if maths is a bit incomplete around the edges, you could argue that it doesn't really matter.
Although Gödel proves it's not possible to formalise all of maths, it is possible to formalise all the mathematics we actually need to use.
Take flying as an example. Now, I did my PhD in the mathematics of aerodynamics, and that means I spent 4 years poring over equations for wing sections and wind speed. It's stuff that I know like the back of my hand. But does that qualify me for going up in one of these on my own? Absolutely not. And on the other hand, these guys don't really need to know any of this stuff to make them graceful acrobats in the air.
Not having a complete understanding doesn't always matter. We've still flown successfully for over 100 years. And now it's my turn.
And then this is your
diagonal
strap that comes across. This will dig in a little bit on takeoff when you're leaning forward and running down the hill.
I can handle it.
It should be a little bit uncomfortable.
I can handle it.
Don't worry too much about it.
And do you have quite a good feel for where the thermals are?
You have to have the right weather conditions. So if you imagine a hill that faces totally into the wind, that's well drained, maybe darker, and it will create this kind of pool of warm air, and then it will, once it kind of reaches a decent temperature difference, it bobbles up through the atmosphere.
Yeah. It's almost like we've got kind of opposing skills.
Yeah.
And like they're sort of about the same thing, but you don't need my skills to do what you do, and I couldn't do what you do.
I guess the ground speed element has a bit of mass in there. Like we always start the lesson with a bit of mass to begin with. Where's the wind coming from? How strong it is? How fast am I going to go if I point into wind?
But you're not solving Navier-Stokes equations, are you?
Don't even know what that means.
Yeah, exactly.
Before the theoretical analysis of aviation came along, the practical side of flying was mere trial and error. Now we have a much more reliable understanding of what keeps us aloft. And it doesn't really matter if the maths behind it is ultimately a bit fuzzy around the edges.
In the real world, the best that we can do is just accept Gödel's incompleteness theorem and get on with life. Hey! It's amazing!
There's the thermal. Yeah. Woo! Much more, a bit stronger.
Yeah.
We have to put aside for the moment the question of whether maths is invented or discovered, because it now looks like we may have to determine which part of maths we are asking about. You see, for me, Gödel's work highlights the distinction between pure theoretical maths and practical applied maths.
So here is how I see things. With mathematics, there's a split down the middle of the subject because the story changes depending on what world you start with, whether it's the real one or one that exists in our imaginations. And right now, when we're flying, this is very much in the realm of applied mathematics, where everything is tangible and practical and a little bit imprecise.
But alongside that is where the more theoretical, pure mathematics lives.
That's where you have your proofs, your paradoxes, and incompleteness theorems. A realm which doesn't match up with a physical reality, a sort of imperfect perfection.
Even though I instinctively feel that maths is discovered, I like that there is this pure theoretical part of maths that isn't found in reality. And since the maths there doesn't need to match reality, It's a convenient place where we can leave all the weird, contradictory bits that we come across. However, I might have it the wrong way round. Although pure theoretical math seems rather divorced from reality, that might merely reflect the fact that reality is not quite what we think it is. And it's a reality that we can uncover through the strange maths of quantum physics.
The weirdest worlds that most of us have come across are likely to be in fiction, such as this, Alice's Adventures in Wonderland. Now, the author, Lewis Carroll, real name Charles Dodgson, was actually a mathematics don at Oxford and a staunch traditionalist.
It's generally believed that much of this surreal story is a thinly veiled satire on the new avant-garde maths that was flourishing when he was writing in the 1860s.
Still feels relevant today and applies equally well to the new weird kid on the block, quantum physics.
Take a close look at the physical world around us, and you can reduce it all to maths. The solid bricks of our houses or the blood cells in our veins can all be reduced down into chemicals, which comprise elements, which themselves are made up of atoms, comprising a tiny nucleus of protons and neutrons and electrons buzzing around in a cloud of mostly emptiness.
The protons and neutrons in turn are built from smaller subatomic particles that we can't directly observe. We can only verify their existence using experiments and mathematics.
As we delve deeper into this world, scientists have discovered something very strange indeed. We can never actually know the precise location of most particles in this subatomic or quantum realm. All we can know is the likelihood of them being somewhere, a mathematical formula that describes the probability of their position.
All of this means we are fundamentally, at the quantum level, just a great fuzz of energy and probabilities. Not sure Lewis Carroll would have liked that.
And the only way to explore this ill-defined quantum world is through mathematics, perfectly equipped to handle strange probabilities.
It seems like there's quite a lot of uncertainty in quantum physics. Does that bother you?
No. When I heard that things were, uncertain and also against our common sense in quantum physics, then I thought like, oh wow, that sounds interesting. I want to know more about that.
The pivotal maths behind the quantum world was first laid out by Austrian physicist Erwin Schrödinger in 1926. His equations accurately describe the unusual behaviour of subatomic particles.
Okay, all right, tell you what then. Quantum physics, lesson 101. Where do we start? Give me a lesson.
Okay, I would say we have to start with superposition. So let's talk about electrons. So they're a very small particle, and they can be in two states. They have a state with spin, and the spin can be pointing up or down. So if we were in the classical world, the spin could only be either up or down. But in the quantum world, the spin is in a superposition, which means it can be up and down at the same time.
Let me see if I understand this then. So superposition is where something is and isn't something at the same time.
Yes, we can think about some examples. So let's say that we have a cup, and the cup is full of water, or that's one state. Another possible state is that the cup is empty. So if we were bringing the quantum ideas to the classical world, we would say that the state, one possible state of the cup would be to be empty and full at the same time.
Okay, which you never see in the world that we're living in. You never see a cup that's full and empty.
Yes, we don't.
But you see this a lot in the quantum world.
Yes, superpositions are an essential part of the quantum world.
Like a light being on and off at the same time.
Exactly, or the cake being eaten or not eaten at the same time.
Okay, it's a very tough idea to get around.
Yes.
Given two possible outcomes, in the quantum world, we now have to allow for a third one, the combination of both outcomes. At the quantum scale, you can have your cake and eat it.
This is such a weird idea. How do we know it's real?
Well, because we've done many experiments to prove it that show exactly that behavior.
What does that experiment look like?
Well, if we put it, say, in terms of things we have here in the table, we could think about, let's say that I want this piece of sugar to come into my cup, but there's this pot in the middle. So then if the sugar is going to come from here to my cup, it could either go this way or that way in the classical world. But in a quantum experiment, it can take both routes at the same time, and I would be able to distinguish that it did that if I did a quantum experiment.
God, this is too weird.
Welcome to my world. So you go through this whole transition from first the ideas and the mathematics, and then up to showing it in the experiment.
What came out of Schrödinger's mass was a prediction of something even stranger that can sometimes be produced when particles interact in the quantum world, a phenomenon called entanglement.
All right, tell me about entanglement then.
Okay, so take two electrons. If the electrons are entangled, and I do something to one of the electrons, I, for example, change the direction of the spin, that will instantaneously affect the state of the other electron, even if they're separated long distances.
How far away are they from each other?
Well, they can be a few centimeters, but now the latest experiments using satellites show entanglement across 1,200 kilometers.
What?
Yes.
You've got something over here, and something at 1,200 kilometers away. You do something to one, and the other one instantly knows what's happened.
Yes, you affect the state of the other one instantly.
Apparently, there is no causal link. The only thing we can say is that the two particles are synchronized.
How does one know what the other one's doing?
Well, that we're still trying to understand, because that's what mathematics tells us, and then we can show it in the experiment, but we're still struggling to understand what that means. And one of the reasons why we don't understand it in, like you're asking, is because we don't see it in our everyday life. So let's say it's not part of our experience and common sense, but that doesn't mean it doesn't happen.
So quantum mathematics has made predictions which have been discovered to be true. But despite that, the quantum world is so weird. It suggests to me that the maths behind it is just invented. It feels like what we're seeing is evidence of a man-made system being pushed too far. These are the absurdities that appear when it's applied to situations it wasn't designed for. But my quest to find the truth about maths takes me back to nature. There is amazing new evidence that quantum processes might actually be crucial to our own existence and much of life on Earth. That would strengthen the arguments that mathematical processes are intrinsic to our world, that maths is discovered. It all comes down to photosynthesis, the process that converts sunlight into chemical energy used in life. It takes place in molecules called chlorophyll, which can be found in plants, algae, and bacteria.
In bacteria, we have something that's similar to what we have in plants.
So this is the stuff that captures the sunlight?
Exactly. Each of these molecules, each of these little blue things here that I'm showing, is a bacterial chlorophyll, and if we take it apart, it will capture light.
The chlorophyll captures light by absorbing particles of light, or photons.
So a photon is absorbed, and is absorbed by all of them. So energy is shared by all of these bacterial chlorophylls. And that sharing, we call it, is in a quantum superposition.
Because it's coming in and hitting one of these, but all of them are somehow...
In a way, it's as if each of the electrons of the chlorophylls are talking to each other and sharing the energy around.
The subatomic particles in the chlorophyll are synchronized in a way that can only be described by quantum mechanics.
Does it do a good job? I mean, is it efficient?
That is part of why photosynthesis is efficient, because by sharing the energy among all of them, it's easier to transfer the energy to another molecule. Imagine if you have to share the energy one by one, you have to explore each path separately. But if you share the energy all together, you explore all the paths at the same time.
Every leaf on every plant on the planet has been following these quantum rules for millions of years, and we still don't fully understand how they do it. Without quantum physics, despite all the mathematical uncertainties and ambiguities, plants wouldn't produce oxygen so efficiently. And without oxygen, we wouldn't exist.
These systems are amazing because they are effectively at the interface between using a little bit of classical mechanics and a little bit of quantum mechanics to operate in a wonderful way.
Ultimately, quantum mechanics is at the heart of photosynthesis and, well, I guess all of life on Earth.
It is. It is. We can say life is nothing but quantum mechanics giving us energy.
So what does all this mean for our key question about the origins of maths? There is no shortage of evidence that mathematical rules are intrinsic to the world. We keep discovering them everywhere. However, we now know we have to take some of that maths on faith, and believing in the numbers is taking us to a very strange world, with crazy notions like superposition and entanglement at the core of it.
Quantum mathematics is inextricably linked to the world as we know it, or as we knew it, because the world is actually a whole lot weirder than we thought. What quantum mechanics does do is force us to question what is real and what is reality anyway.
Just how much light can mathematics shed on reality? With the world stripped bare, exposing the nuts and bolts of existence, what does maths tell us about this realm of subatomic particles?
The maths that underlies it isn't particularly pretty, but it can all be written out in just one equation.
This is the formula that describes the constituents of the universe. It has become well enough accepted to be called the standard model of subatomic physics.
I told you it wasn't pretty. Now, you're just going to have to take my word for it on this one. This equation encapsulates all of the fundamental properties of the subatomic world.
But there are a couple of sticking points.
For one thing, no one has ever satisfactorily explained how our common sense, day-to-day version of the world emerges from this kind of subatomic reality. All of that fuzziness, all of that uncertainty in the quantum world, just how does it end up giving us that comfortable, familiar solidity of the normal world?
At the other end of the spectrum, the solar system and beyond is beautifully and accurately described by a different equation: Einstein's general relativity.
This remarkable equation tells you about gravity, about the warping of space-time, about general relativity. And when you take these two together, these two single mathematical sentences, they're enough to tell you everything you need about the fundamental behavior of the universe and everything in it. There is nothing more articulate than mathematics.
maths seems to be written into the physical universe.
So on the one hand, at the teeny tiny scale, the standard model of particle physics does this amazing job. And in the ginormous scale, general relativity, I mean, you couldn't ask for anything more. There's just one problem when you try and put these two together. They're incompatible.
The problem is that general relativity breaks down in the quantum world. Gravity simply doesn't apply to particles at the subatomic scale. Meanwhile, quantum effects are virtually never seen at the scale of humans and planets where gravity rules. You and I are never in a superposition of existing and not existing at the same time.
So what does this mean for us? Are there two different worlds, each obeying their own set of mathematical laws? Solving this conundrum is one of the biggest problems that puzzles scientists today.
Will we ever reconcile the two?
I think it's perfectly plausible that within our lifetime, somebody, maybe somebody watching this program, will discover the mathematical structure which unifies Einstein's theory of relativity with quantum mechanics and just provides a perfect description of this world. And that would be really exciting.
Will we have one? How do I know? We would all like to have one, but maybe we are not smart enough to formulate a theory that combines everything. It's hard.
I do believe that there are good ideas out there and that eventually, it might take a long time, but eventually humans will work this out. I'm confident about that.
So will we make it all the way to include all possible forces at all possible scales with all possible forms of matter? It's a hope I have for our species, and that's all I can say.
The incompatibility of these two great theories, general relativity and quantum mechanics, creates a serious obstacle for believing that maths is really discovered. And there's a bigger hurdle to come. Many of the best proposals to unify general relativity and the quantum world have consequences that are even weirder than the problems they're trying to solve. They predict the existence of multiple universes. This idea is rooted in the mathematical explanations of the quantum world and the work of its founding father, Erwin Schrödinger.
The mathematics in Schrödinger's equation insists that particles can exist in multiple states at the same time. And Schrödinger himself says that these possibilities aren't just alternatives, but really happen simultaneously.
This can lead to multiple universes, and the maths also suggests there's an infinite number of them, each slightly different from the others.
Thank you. Mathematically speaking, in an infinite universe, everything that's possible has to happen somewhere.
Yep, that's right. Everything possible happens somewhere. Even Schrödinger acknowledged that the consequences of his equation describing the quantum world might seem lunatic.
But if there's one thing I've learned, is that you should trust the maths. So maybe our experience isn't special. Maybe our reality isn't unique after all.
There are so many distinct avenues of investigation that lead to the possibility of a multiverse. From our studies of unification and string theory, from our studies of quantum mechanics, even from the study of space going on infinitely far. Even that gives rise to a version of the multiverse.
If we're going to reject everything that just seems weird, we're almost guaranteed to reject the true theories of the future when they get discovered. I think we should just chill out, accept that the world is weird, and that's just part of its charm, and trust the math.
So why does all of this matter? Well, if maths really is discovered, then there is an intrinsic truth behind the maths we uncover, however weird that truth seems to be. If maths is invented, then how do we know what is true or false? Is it true purely because we define it so? And how does it relate to the real world that we all experience?
368 look good in the full thrust mode.
In this series, we've seen that maths can explain so much of our world, from aerodynamics to planetary orbits, from the subatomic world to processes crucial to life on Earth. And that is something I just can't accept as a coincidence.
So here's my take on things. For me, it's almost as though you have this alternate, parallel mathematical world that hides just beneath our own. You can't see it, you can't touch it. The only way that you can explore it is by using the language that we've invented. All of those symbols and equations and conventions are our only tools of navigation, and they are undoubtedly man-made. But once you're inside that world, once you're exploring the landscape that mathematics has laid out in front of you, I am absolutely convinced that you are on a voyage of discovery. It is a world without a human designer. So ultimately, I think it's both. Mathematics is a little bit of invention and a lot of discovery.
Mathematicians will probably never all agree, and maybe we will never find a definitive answer. But the consequences of having that debate is why it really matters.
We have used mathematics for a much deeper understanding of nature and of the universe in general. We know about the universe now things that a few hundred years ago people didn't even know what to ask.
Searching for the truth about maths has, over 2,000 years of history, transformed the human experience. Discovering patterns everywhere in nature has given us structure, beauty, and inspiration. Inventing new areas of maths has led to an explosion of technology that ultimately underpins modern trade and computing. We have discovered powerful rules that we continue to use to explore, enhance, and explain the world around us. And we have had a tantalizing glimpse of what could be to come.
It's quite possible that what we have been doing in science for all these centuries is, in some sense, looking for our keys under the lamppost. We have been able to use mathematics to describe what happens out there, but that could be the tip of an iceberg of reality that we, as yet, don't have any understanding of, haven't yet had any contact with.
But most of all, I think that asking questions about the origins and truth of maths has given us a purpose. It's given us understanding.
Ultimately, maths has given us meaning. What is it that makes our world work the way that it does? Explore more about the magic and mystery of mathematics and how it impacts our everyday lives by going to the web address below and following links to the Open University.
Tomorrow, Brian Cox wonders if we will ever find aliens. Human Universe is here at 8. Next tonight on BBC4, David Livingstone and the missionaries who changed the face of empire.